Okay, so a couple of minutes ago we were looking at the factors that affect whether a reaction would partition SN1 along the SN1 pathway or the SN2 pathway. And we saw that it would depend upon the nature of R, the nature of the substrate, right? Nature of R, nature of X. It would also depend upon the nature of the nucleophile. And we've looked so far at, we said that it's a matter of timing. That if we had a great nucleophile, we tend to get SN2. If we had a good nucleophile, we tend to get SN1. So the question is, what makes a nucleophile great? What makes a nucleophile good? And the answer is really quite simple. If I wanted to measure, if I wanted to determine which person in the class was the highest jumper, I could either put a barrier, a ruler or something, 1 foot off the ground, or I can put it 5 feet off the ground. And if I put it 1 foot off the ground, that's not a good judge, it's not a good way of determining who's the best jumper, because everybody can jump over a foot. If I put it 5 feet over the ground, then only the best high jumpers will be able to make that. And so by raising the bar, by making the task more difficult, it is a better way of screening who is good at something and who is not. So if I want to determine which nucleophile is a strong nucleophile, which is a weak nucleophile, I have to make the task difficult. And of the two options, SN1, where you attack a carbocation that is flat, or SN2, where you attack a delta plus carbon that is sterically hindered, the SN2 reaction is more difficult. So if I want to determine which nucleophile is better than the other, I need to use as my yardstick the SN2 reaction. Right? The SN2 reaction will be my yardstick for nucleophilicity. So what must happen in the SN2 reaction? The answer is, we've seen this a little while ago, that in reality, bond formation, or covalent bond formation, involves the overlap of orbitals. I'm going to show these orbitals like so for now. This is my Rx, and my nucleophile must be able to deliver these two electrons to this orbital. Okay? Well, that's going to be made difficult, A, by the fact that carbon only has a delta plus charge, but also there are groups, whatever the size is, that may be in this area that will make the approach of the nucleophile difficult. So which nucleophile would be good at delivering the package? And the answer is the one that can do it without getting so close to the carbon that it starts to feel these alkyl groups. So how will that be accomplished? And the answer is, if a nucleophile has a large orbital, then two things would be true. Those electrons would be far from the atom's nucleus, therefore they'll be loosely held, therefore they'll be easily given up. And two, if the orbital is large, it means the atom does not have to approach anywhere as near to the carbon to deliver the package. So if I have a nucleophile with a small orbital, it has to get darn close in to this site to be able to deliver the package, for overlap to start to occur. That brings the body of the nucleophile to a point where it begins to interact with my groups. On the other hand, a nucleophile with a large orbital, a long orbital, can begin bonding with the carbon at a larger internuclear separation. And that means the nucleophile will not approach the site, right, will not approach the site close enough for it to start to feel whatever groups are present on this site. So in general, the longer the orbital that the nucleophile is using, the more nucleophilic it is, the more effective it is as an electron pair donor. So what we're saying then is that the longer the orbital, the more nucleophilic. What it really translates to is the bigger the atom. Because, for example, a fluorine atom would use a 2p orbital, which is about this long. Chlorine will use 3p, which is that long. Bromine, 4p, that long. Iodine, 5p, that long. So as the atom gets bigger, the nucleophilicity gets larger. In fact, what we say is, as the leading atom gets bigger, the nucleophilicity increases. So what we really want to look at then is what's called nucleophilicity. We want to look at the factors that affect nucleophilicity. In other words, the nucleophilic character of a species. And those factors are: one, the size of the leading atom. And what do I mean by leading atom? The leading atom is the atom that leads the charge, that actually delivers the electron pair to the electrophile. The bigger that is, the more nucleophilic. So in other words, iodide, more nucleophilic than bromide, more nucleophilic than chloride, more nucleophilic than fluoride. Okay. 2 is the overall size of the species. Right? So what does that mean? Well, if you look at a series of nucleophiles, let's say I look, for example, at HO minus versus MEO minus versus, let's say, isopropoxide versus T-butoxide. Each of those species is nucleophilic. And they all are using the same leading atom, which is oxygen, which is O minus. But it's not just the oxygen only that's going to be involved in chemistry, it's the oxygen and its entourage. And obviously, the smaller the entourage, the less steric hindrance the species encounters in approaching this carbon. The bigger the entourage, the more difficulty there is, the more steric difficulty, the more steric hindrance to the approach. So in other words, hydroxide, which only has an H as its entourage, is going to be very effective at getting into that narrow space, whereas T-butoxide would be horrible at getting in because the T-butyl group is huge. So although the larger atom, the larger leading atom, is the more nucleophilic, now the smaller overall size becomes a better nucleophile. So bigger is better for the leading atom. Smaller is better for the entire species. Okay? So hydroxide is the superior nucleophile, T-butoxide is the worst. So that's 2 factors. The third factor that affects how nucleophilic something is the charge. If, for example, I were to look at, say, hydroxide versus water versus H3O+, and I ask you, which of these is the stronger nucleophile? That's an easy question. What must a nucleophile do? The answer is it has to deliver an electron pair. When will this O deliver electron pair most effectively? When it has 3 lone pairs and a negative charge, when it has 2 lone pairs and is neutral, or when it has 1 lone pair and is positive. And the answer is, hands down, when I have 3 lone pairs compressed in a small area and a negative charge, the impetus is to get rid of a lone pair, which means it'll get rid of the charge. If I have 2 lone pairs around a small atom, that's electronic repulsion, which will then force the electron pair off, make it nucleophilic, but it's not going to be as desperate to get rid of a lone pair as it is in hydroxide. Okay? And then finally, H3O+, although it has a lone pair and is potentially nucleophilic, would be a poor nucleophile because there isn't a huge amount of electron pressure, right? Because there's only 1 lone pair. And secondly, the O is positive. So in general, the more negatively charged the atom is, the more nucleophilic it tends to be. The more electronic compression there is, the more electron pairs there are in a small area, the more nucleophilic the species tends to be. So those are the factors then that affect what we call nucleophilicity. So with that in mind, I can go ahead then and say, well, what makes great nucleophiles? What makes good nucleophiles? Well, great nucleophiles include things like iodide. Let's see. So iodide, anything with sulfur, so thiolates or even H2S, these are great nucleophiles. Species like azids are also great nucleophiles. Cyanide is also a fantastic nucleophile. And acetylids are also fantastic nucleophiles. It turns out peroxides, hydroperoxides, are also great nucleophiles. So the 1, 2, 3, 4, 5, 6, 7 species I just gave you here are called super nucleophiles. They are very, very aggressive nucleophiles. Good nucleophiles would include things like bromide, which really is kind of between great and good, chloride, hydroxide, is a good nucleophile. Alkoxide, a great nucleophile. Carboxylate is a good nucleophile, and the textbook will have a whole bunch of others. So there are some great nucleophiles which will strongly encourage SN2. There are good nucleophiles which will tend to encourage SN1. So let's put things back in context to see where we are. We are looking at the factors that are affecting SN1 and SN2. Right? And we saw the factors were the substrate, right? And we looked at the nature of R and the nature of X. Right? When R was methyl and primary, SN2. When R was tertiary, SN1. When R was secondary, SN1 or SN2. We looked at the nature of the leaving group. If X was a great leaving group, we tended to get SN1. If X is a good leaving group, we tend to get SN2. The other factor was the nucleophile. And we looked at the nucleophile in terms of its strength. Right? And we said great nucleophile tends to give SN2. Good nucleophile tends to give SN1. There's another factor we have to look at with a nucleophile, and that is its concentration. And that's very easily interpreted, because if I look at the rate equation for the SN1, it is rate is equal to K times the conc of Rx times the conc of the nucleophile. In other words, for heaven's sake, it's SN2. In other words, in the SN2 reaction, the nucleophile's concentration features in the rate equation. For the SN1, rate is equal to K times conc of Rx. So the nucleophile's concentration does not feature in the rate of the rate equation for the SN1 reaction. Why is that important? It's important because let's say I mixed, say, 1 molar Rx, okay? And I want to get the reaction to be SN2. What I want is the rate of the SN2 to outstrip the rate of the SN1. In other words, I want the SN2 reaction to be so fast, the SN1 reaction can't compete. So how would I do that? If I already have 1 molar Rx, how can I make the rate of the SN2 reaction outstrip that of the SN1? The answer is, make the nucleophile concentration huge. So if I make my nucleophile concentration 5 molar, then the rate of the SN2 reaction will be huge, because it's 5 times 1, and we're going to leave K out for a second. Whereas the rate of the SN1 will still only be 1, because the the concentration of Rx is 1 molar. So if I want to make the reaction SN2, I will use a high concentration of an aggressive nucleophile, a strong nucleophile. Strong nucleophiles encourage SN2, high concentrations encourage SN2. Suppose I want the reaction to be SN1. How would I do that? You would notice the rate equation for the SN1 does not have the nucleophile concentration in it. That's okay, because the SN1 and SN2 reactions are in competition. So I could make the SN1 reaction win by sabotaging the SN2. And how would I do that? I would do that by using a very low nucleophile concentration. So let's say we're running 1 molar Rx. If I use 0.1 molar nucleophile, then the rate, and I'm just for now, let's say the rate constant is just not a factor, it's unit or whatever. If I use 0.1 molar nucleophile, it means the rate for the SN2 reaction will become 0.1 times 1, which is 0.1. But the rate for the SN1 remains 1. So in other words, the SN1 is now 10 times faster than the rate of the SN2. So the fact is, when I have two features, when I've got two systems in competition, I've got two things that are in competition. I can make this thing win by making it much better than the other. Or I can make it win. What was I saying? Yeah. So I can make this thing win by making it much bigger, much better than the other, or by making this one worse. And the typical analogy, I guess a good analogy is, if I have two politicians vying for office, I can say politician A takes half his salary and gives it to the poor. He kisses babies and he helps old women cross the street. So politician A is a much better candidate. Politician A wins. Or I can say politician B steals from little old ladies, kicks babies and and steals from whatever. So if I make politician B really bad, politician A wins. So politician A in the second scenario didn't have to do anything. I could mudsling politician B and have politician A win. And it's exactly the same thing. The rate of the SN1 is not affected by the nucleophile concentration. But by changing the nucleophile concentration, I can either promote SN2 at high nucleophile concentration or promote SN1 at low nucleophile concentration. So I can wrap that up and say, if I want SN2, I will use a high concentration of a strong nucleophile. 3 molar cyanide, 4 molar iodide. If I want to do SN1, I will use a low concentration of a modest nucleophile. 0.1 molar acetate, 0.2 molar chloride, and so on. So that's the nucleophile. The third factor that affects partitioning of a reaction between SN1 and SN2 is the solvent. Okay? And we're going to look at solvent in just a couple of ways. I'm just going to spend 10 more minutes on this and then we'll finish. We can look at the solvent in terms of A, its polarity, okay, and B, its proticity. Okay? Okay, so let's see how polarity works. And polarity is a kind of a funny issue. So we will only get SN1 in polar solvent. We'll only get SN reactions of any kind, SN1 or SN2 in a polar solvent. Why is that? Well, if I look at the typical SN reaction, my substrate is Rx. My substrate is polar. Polar substrates will only dissolve in polar solvents, right? Because polar substrates do dipole-dipole bonding, they will form dipole-dipole bonds with the solvent, and so I'm going to get solubility. Polar compounds will not dissolve in hexane, because I'll be swapping dipole-dipole bonds for van der Waals bonds, will not work. So if I can't be in solution, I can't do chemistry. So the solvent needs to have a threshold polarity for my substrate to dissolve to get chemistry. Often my nucleophiles are negative. They're cyanide salts, sodium cyanide, sodium iodide, potassium acetate, potassium bromide. These are salts. These are ionic compounds. Ionic compounds will not dissolve in nonpolar solvents. So SN reactions in general must occur in a polar solvent, because that way I get both my substrate and often my nucleophile to dissolve. So, has to be polar. But there's an issue, and the issue is the more polar it gets, so there's a certain minimum polarity needed for any SN. But the more polar it gets, the more I encourage SN1. So why is that? And it's a really very subtle discussion point. Right? So it goes like this. Let's assume I have Rx, right, which is a delta plus and a delta minus. And Rx has to, oh my God, Rx has to ionize to make R plus X minus. Okay? My transition state for the SN1 reaction looks like this. We mentioned that in class today. I'll have R delta plus 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 plus, X delta minus 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 minus. In other words, the transition state for the SN1 reaction is more polar than the ground state, than the substrate molecule. What is polarity measured in? Polarity is mu, is the size of the dipole times the bond length. The dipole is much bigger in the transition state. The bond length is much longer. So it's a no-brainer. The transition state is more polar than the ground state. That's the SN1 reaction. What about the SN2? In the SN2, I have a negative nucleophile as a discrete species attacking R delta plus X delta minus. The reaction goes via a transition state, right, to give rise to my product, and for now I'm going to draw the product here, which is going to be nuc R and then X minus. So what does my transition state look like? Well, it's nuc dot 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 R dot 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 X. My minus charge is now distributed between the nuc and the R. So here I have a discrete point charge in my nucleophile. Here it's smeared over a pretty large distance. And so this entity is actually less polar than that entity. So in the SN2 reaction, the transition state is less polar. In the SN2 reaction, the ground state is more polar. In the SN1, the transition state is more polar. So let's imagine then I run an SN1 reaction in a solvent like ether. And ether is a polar solvent, modestly polar solvent. Let's change the solvent from ether to something like DMSO. DMSO is this, or let's say acetone. You've met acetone. This is acetone. Acetone is a very polar solvent, not only because I have carbon bond to O, but I've got a resonance form that looks like this, and that accentuates the polarity of acetone. So let's run the reaction instead in acetone. What happens? Acetone is polar. So acetone will stabilize the ground state of my reaction. So I'm going to take my pen now, and I'm going to make my pen red. So when I use acetone as my solvent, my species now falls here. And this makes perfect sense. If the solvent is more polar, I will form stronger solvent-solute bonds, right? And therefore I would stabilize the species. As the bonds get stronger, the system gets more stable. But what happens to my transition state in acetone? My transition state is even more polar than the ground state. So when my transition state is forming in a very polar solvent, it is stabilized even more. So my transition state ends up being here. Not to mention, my product, which has R plus and X minus, is going to end up somewhere here. I'm not so interested in the product. So what it means is my new reaction profile diagram now looks like this. In other words, my activation energy barrier for the reaction is now here, as compared to what it was at the beginning, which is here. So if I move from a less polar solvent like ether to a more polar solvent like acetone, my activation energy barrier falls for the SN1 reaction, and therefore the rate increases. So I need to have a polar solvent to get any SN chemistry. But the more polar I make it, the more I encourage the SN1. You can do an analysis on the SN2 and indicate that in fact the effect is actually opposite for the SN2. So in general, what I can say then is, the more that I need a minimum polarity for SN1, and the more polar it is, the more I encourage SN1. What about proticity? In fact, what does proticity mean? Proticity refers to whether a solvent is protic or not, whether it's protic or not, and it's protic versus aprotic. A protic solvent is simply one that can hydrogen bond. So protic solvents include water, alcohols, amines, carboxylic acids, amides, and so on. Aprotic solvents are things that cannot hydrogen bond. So for example, acetone is an aprotic solvent. We talked about DMSO. DMSO looks very much like acetone. Right? This is called DMSO. Right? That is it's called dimethyl sulfoxide. That's a protic solvent. This compound is called DMF. Right, this compound is called DMF. Right, so this is DMF. Which is an acronym for dimethyl formamide, right? This is the formamide group. So these are aprotic solvents. They do not have H bonds to N, O, or F. But these protic solvents are actually polar and aprotic. There are solvents like benzene, cyclohexane, hexane, and so on, carbon tetrachloride, These are also aprotic, but these are non-polar aprotic. Now, all protic solvents are polar, so it is superfluous to say polar protic. If you're protic, you're polar. For heaven's sake, you've got H bound to O, H bound to N. You're going to be polar. So all protic solvents are polar. But I can divide aprotic solvents between those that are polar and those that are non-polar. Okay? Now, I'm only interested in our discussion in the polar solvents. In other words, the protic ones, which are all polar, and then the polar aprotic ones. Because to get SN, I need to have a solvent that is polar. So what role does a solvent play in the partitioning of a reaction between SN1 and SN2? And it's a point I didn't make earlier, which I need to make now. And that is, if you notice how we listed our factors, we said the substrate was the first factor, nature of R was first, nature of X. Nucleophile, strength and concentration, and then solvent. Those factors are listed in descending order of priority, and we saw that. The nature of R fixed the reaction. The next most important factor is the leaving group. The next most important factor is the strength of the nucleophile. The next most important factor is the concentration of the nucleophile. And the solvent proticity is the third most important, is the last factor down the list. So whereas, for example, this factor gross tunes the course of the reaction, these with descending importance fine tune it. Okay? And there's another point I forgot to mention. A lot of people ask, what do I mean by high concentration of a nucleophile? The answer is, usually anything that is a 5-fold excess is considered a high concentration. So if I had 0.1 molar substrate, 0.5 molar nucleophile is a high concentration. Sometimes we run with 1 molar substrate, and so you tend to use a 3, 4, 5 molar material. So if you have a 5-fold excess, that's considered to be high concentration. All right. What about proticity then? Well, the answer is really very simple. In the SN2 reaction, what is required is that my nucleophile approach from the backside and do the attack. Okay? That's the essence of the SN2 reaction. Well, when I put my nucleophile in solution, it is not naked. Right? The nucleophile is built in with the solvent jacket around it. And if I put my nucleophile in the presence of a polar protic solvent, like water or an ethanol and so on, the polar protic solvent hydrogen bonds to the nucleophile. And I end up with a very thick, tightly bound solvation shell. So I have layers and layers and layers of solvent molecules jostling for position around the nucleophile. This is my nucleophile in a polar, well, in fact, I don't need to say polar, I can just say protic, because if you're protic, you're polar. If I take that same nucleophile and I dissolve it in a polar but aprotic solvent, my solvation jacket is nowhere near as thick as it is in a protic medium. So this is how it is in a polar aprotic system. So two things are true. The solvation shell around the nucleophile in a protic solvent is thicker, and the solvent is more tightly bound. The solvation shell in a polar aprotic solvent is thinner, and the solvent is not as tightly bound. So let's imagine then I dissolve my substrate in my solvent. And I have my nucleophile in solution. If I'm running the reaction in a polar protic medium, there are several problems. First of all, my nucleophile is heavy and encumbered, so it moves very lethargically through the solution. What happens then is it gives the substrate time to acquire energy by collision, get enough energy to ionize and give me SN1. So because my nucleophile is very big and heavy, it moves very slowly. My substrate can ionize and go SN1. But what's worse is that if this nucleophile were to approach this carbon, well, the thing is huge. So there'll be massive steric hindrance to the approach of the nucleophile, right? Because there might be substrates like groups here. and there'll be steric hindrance to the approach of the nucleophile, which is going to make the reaction difficult. Not only is that bad, but my nucleophile wants to deliver this lone pair of electrons to the carbon. But if there are layers and layers and layers and layers of tightly bound solvent molecules, I must now strip those solvent molecules away from the nucleophile so the nucleophile can interact with the orbital on the carbon. That's going to be difficult if my nucleophile is tightly bound to many, many layers of solvent. So all of this stuff makes the SN2 reaction in a protic solvent very difficult. What happens if it's polar and aprotic? Well, there certainly is a solvation jacket around the nucleophile. There must be for it to dissolve. But the species is fairly light and fleet-footed, so it moves to solution very rapidly and encounters the substrate probably before it has time to ionize by collisional activation. Secondly, once it gets into docking range, I just need to divest it of that much solvent. Not a lot of solvent, and plus, then it's not tightly bound. So it's very easy for a nucleophile in a polar aprotic solvent to undergo SN2. So what this means then is, as far as proticity goes, protic solvents discourage SN2, which therefore means they will encourage SN1. And if I take that back, they discourage SN2, and by default it means SN1 is a default reaction. It doesn't encourage SN2, it just discourages SN1. And it turns out to be equivalent, but it's not quite the same. Whereas if I had an aprotic solvent, but it has to be polar, an aprotic but polar solvent would tend to encourage the SN2 reaction. Okay? So I have a list of several factors that will affect the partitioning of a reaction between SN1 and SN2. And that would be pretty much it. And so we'll stop here, and when we start 302, which is for some of you guys in a couple of weeks, others a bit longer, we will pick this up a little bit in some more detail and then move on to a few other issues. Okay, so thank you guys very much, and have a good rest of the day.